lesson 27 is relationship between ratios. 27.1 introduces the trig ratios, so sine, cosine, and tangent. Starting up at the top, the lengths of the sides of a right triangle have three important ratios called sine, cosine, and tangent. The ratios are related to the acute angles, and they can help you find missing measurements in right triangles. So before we get started, it's important to just kind of note that usually instead of writing out sine, cosine, and tangent, those words are typically shortened by using the first three letters in each word. So sine would just be S-I-N, but you still read it as sine, not sin. And then cosine is C-O-S, cosine, and then tangent, T-A-N. Instead of saying like tan, you would still typically say the full word tangent. We just shorten them into the first three letters when we're writing them. So the formulas for each, they involve phrases like opposite leg, adjacent leg, and hypotenuse. Hypotenuse we've talked about, but with the other ones, they may not sound super familiar yet, but we'll get into them with the first example. It's just important to kind of get the formulas down before we get started. So sine is opposite leg of an angle over the hypotenuse from the triangle. Cosine is the adjacent leg over the hypotenuse. And then tangent is the opposite leg over the adjacent leg. So there is a trick that we use to kind of remember what each of the formulas or ratios are for sine, cosine, and tangent. It's called SOHCAHTOA, and it's just a way of like kind of organizing the formulas together. So it's SOH, and that stands for sine. So S is opposite leg, so O over the hypotenuse, so H. So that's what the SOH is. Sine is opposite over hypotenuse. And then the second part is CAH, and that is that cosine is the adjacent leg over the hypotenuse, so A over H. So CAH is cosine is adjacent over hypotenuse, and then the last part is TOA. And that's T for tangent is the opposite leg O over the adjacent leg A. So TOA is tangent is opposite over adjacent, and then altogether it's SOHCAHTOA is like just what we kind of like read it as, and it's usually just one of those things that kind of helps stick in your head and help remember the order of all of the formulas. And it's important to know like each little set of like three letters is its own trig ratio. So like the first one is S for sine, the second one is C for cosine, and the third one is T for tangent. Okay, so example 1 and example 2 are both going to be using this triangle on the right here. So example 1, we're going to find sine, cosine, and tangent of angle A, so over here. And then example 2, we'll pretty much do the same thing, but we'll switch to angle B. So we don't really use sine, cosine, and tangent for the right angle. They are for the acute angles of a right triangle. And that's what's kind of mentioned up here. The ratios are related to the acute angles. Okay, so for example 1, before we get started, we need to kind of go through and like figure out, okay, what does opposite leg mean? What does adjacent leg mean? And then of course we know hypotenuse is like the longest side of a right triangle. So in this triangle, the hypotenuse is AB. So it's always the longest side, and then it's also the side that is opposite of the right angle. So in this case, it's AB. I'm going to go ahead and label it as hypotenuse. And then between opposite leg and adjacent leg, so the sides of a right triangle that are not the hypotenuse, the general term for them is leg. So these are the two legs of the triangle. And then in terms of opposite or adjacent, opposite means it's on the opposite side of the triangle. So like if I were to take angle A and draw a kind of arrow pointing to the opposite side, it would point at the opposite leg. So that means that BC is going to be the opposite leg from angle A. And then adjacent means next to, so it's the leg that helps create the angle. So for angle A, the leg that helps create it would be AC. So I'm going to label this as adjacent. And then I will say a lot of times, like it's easier to figure out what hypotenuse is and then figure out the opposite leg and then find adjacent last, because sometimes that's the hardest one to figure out. but each acute angle is made up of two sides. It'll always be the hypotenuse and the adjacent leg. So whichever one is not the hypotenuse must be the adjacent leg. Okay, so now example 1. Sine of angle A. So especially as you're first getting comfortable with sine, cosine, tangent, it's helpful to just go ahead and like kind of write reminders of the formula. So sine is opposite leg over hypotenuse. So we write it as O over H for short. And then the opposite leg, we already went ahead and labeled all those sides on our triangle, so it makes it a little bit easier to go and find it. But the opposite side was 3, so we'd put a 3 in the numerator, over the hypotenuse, which was 5. So 3 over 5, and sometimes you'll write your ratios as decimals too, so it's important to know how to change from a fraction to a decimal. You would divide the numerator by the denominator, so in this case we would do 3 divided by 5, which is 0.6. And then the next ratio is cosine. So we'll do cosine of angle A. Cosine is adjacent, so A over hypotenuse H. So for angle A, the adjacent side is a 4. So we'd put a 4 in the numerator. Over the hypotenuse, that doesn't change regardless of our trig function. It's always 5 for this triangle. So it'd be 4 over 5, and if I change that to a decimal, it'd be 0.8. And then the last trig ratio, tangent of angle A. Tangent is opposite, so O over A. Opposite of angle A, that was the 3 right here. And then over adjacent to angle A was the 4. So 3/4, and then if I change that to a decimal, it'd be 0.75. And then example 2 is going to look really, really similar. We're just finding the sine, cosine, tangent of a different angle. So before we really get started with example 2, I want to kind of point out the fact that if I change angles, so like let's say I change my focus to angle B right here, then the labels that I have on the triangle no longer make sense. Because if I try to figure out, okay, what is opposite of angle B, and I use the same approach of drawing an arrow through angle B or across the other side, it's pointing at the adjacent leg from example 1. And that's because if you switch acute angles, the sides are going to switch also. So the opposite and adjacent side are going to switch depending on what angle you're using. So it's really important to know that, because depending on what angle you use, the opposite or the adjacent side could be potentially different. So I'm going to go ahead and relabel these now since we're working with angle B. So angle B up here now. If I want to find my opposite side, like I said, I'll just draw an arrow straight from it pointing to the other side of the triangle, and it's pointing at the 4. So now the 4 is going to be my opposite. And then the adjacent side is the leg that helps create the triangle. Notice I didn't bother to erase hypotenuse because the hypotenuse is a stagnant part. It does not change. It's always going to be the longest side. And then the leg that helps create the angle B is this side BC. So that's going to be my adjacent side. And adjacent just, what? Okay, sorry, I combined like a D and a G, that looked weird. Adjacent just means next to. So it's the leg that's next to angle B. Okay, so adjacent is 3, opposite is going to be 4, hypotenuse is still 5. So for angle B, first we'll find sine of angle B, which sine is opposite over hypotenuse. So we look at the opposite side, which for angle B, the opposite side is 4. So we put a 4 in the numerator. And the hypotenuse is still 5, and then 4/5, if I want to put that as a decimal, would be 0.8. And then the next one, cosine of B. Cosine is adjacent over hypotenuse. So the adjacent side to angle B is that 3, so it'd be 3 over the hypotenuse, which is still 5, and then 3/5 as a decimal is 0.6. And then for tangent of B, tangent is opposite over adjacent, so the opposite side 4 over the adjacent side 3, so 4/3. And then if I change 4/3 to a decimal, it's technically one of those ones that kind of repeats forever, so we could write that as either 1.3 with a bar over it, or you could, if you needed to round, you could do like approximately 1.3 or 1.33, depending on how many decimal points you needed to round to. Okay, so example 3. If you know the ratio for the sine, cosine, and tangent of an angle in a right triangle, you can use it to find the other two ratios. Consider triangle XYZ, that is the one that's down here, with the right angle at angle Z. So if you know that tangent of y is equal to 7 over 24, you can use that information to find sine and cosine of angle y, so that's exactly what we're going to do. So I'm going to rewrite the ratio that we know. So tangent of y is equal to 7 over 24. And then I'm going to use the formula for tangent to help me find missing values in my triangle. So tangent is opposite over adjacent. So then I have to go and find angle y, which is right here. And then it says that the opposite side is 7. So I'm going to find the side that's opposite of angle y, which is xz, and I'm going to put a 7 there. And then the adjacent side is 24, so I need to find the leg that's adjacent to angle y. So there's two sides left. It's kind of helpful to point out, like, okay, the longest side, the one that's opposite the right angle, is the hypotenuse. So the hypotenuse is only called the hypotenuse. It's not going to be the hypotenuse and the adjacent side or and the opposite side. So hypotenuse is the hypotenuse, it's yx. That means that yz is the adjacent side. So this is going to be my adjacent. And because it says adjacent is 24, I'm going to put a 24 there. And then now I have two sides of a right triangle. So if I have two side lengths of a right triangle, I can find the third one using Pythagorean theorem. So Pythagorean theorem, that's a squared plus b squared is equal to c squared. So I know the two legs. I don't know the hypotenuse, so that means I'm going to have to solve for c. So I won't put anything in for c. I'll put the legs in for a and b. It does not matter which one goes where, so I'm going to put 7 in for a, and I'll put 24 in for b. So 7 squared for a squared, and then b squared is going to be 24 squared. And then that's equal to c squared. We have to square both numbers first before adding them together. We couldn't like add them first and then square them. Think order of operations, exponents before addition. So 7 squared is 49. And then 24 squared is 576. And then that's equal to c squared. And then 49 plus 576 is 625. It's equal to c squared. And I need to get just to c because that's going to tell me what my hypotenuse is. So to cancel out the exponent, I have to square root both sides. And then typically when we're solving, when we take the square root, we would include the positive and negative version. So I would say like the square root of 625 is positive or negative 25. But this is referring to like the side length of a triangle. So a side length can't be negative, it's a distance. So we would just take the positive version. So we'd say c is equal to 25. So the hypotenuse is 25. And then now that I know the hypotenuse, I can find sine and cosine of y. Because if both those ratios include hypotenuse in their formula, so I needed to find that. Really, in order to be able to write all three ratios, and we already have one, but to write all three, we need all three sides. Okay, so for sine of y, so sine is opposite over hypotenuse, and we already kind of labeled, oops, I guess I forgot to label the opposite side, but the side that's opposite of y is the 7. So I would put 7 in the numerator, and then over the hypotenuse, which is 25, that's one we just found. And then cosine of y is adjacent over hypotenuse, which the adjacent side is 24, over the hypotenuse, which is 25. So sine of y is 7 over 25. Cosine of y is 24 over 25. So one thing I want to point out is that you can technically have a triangle that is a different size than the one we drew here that has a ratio, a tangent of 7 over 24. because if you have a similar triangle that's say like double in size or triple in size, it could have double, triple side lengths and still have the same tangent ratio. So like, for example, if I had a triangle that was double the size of the one we drew here, its tangent ratio would be 14 over 48. But 14 over 48 simplifies down to 7 over 24. So I was able to use this triangle to find the sine and cosine of any possible triangle because they would all be similar. And so all of their sine, cosine, tangent ratios, they would reduce the same exact way. So just kind of one thing I wanted to point out is that we didn't find necessarily like the exact dimensions of this triangle, but we did kind of find the proportional dimensions, if that makes sense, meaning that no matter what, the triangle would be similar to this one and the sine and cosine would reduce the same way as our answers did. So 27.2, which is complementary angles and trig ratios. So rule up at the top, if one angle in a triangle is a right angle, then the other two angles are complementary. And complementary means that they add up to 90 degrees. So if we use this little graphic here on the right, it says the measure of angle x plus the measure of angle y plus 90 degrees is equal to 180. Because if I take this kind of as like an equation and I were to solve it, let's say I were to subtract over 90 degrees, and then I would bring down the measure of angle x plus the measure of angle y. The 90 minus 90 would be 0. And then 180 degrees minus 90 degrees would be 90 degrees. So you have your 90 degree angle, and then the two remaining angles, angle x and angle y, add up to 90 degrees, which by definition that means they're complementary because they add up to 90 degrees. Okay, so knowing that kind of comes in handy when we are finding like kind of trig ratios a bit. So I want to kind of help, I guess, identify a pattern. So I rewrote the formulas of the top. Those are just for reference. You don't have to write them down again. But example 1, find sine and cosine of each acute angle in the triangle. And it's this triangle to the right that has 5, 12, and 13 as the side lengths. So I'm going to say that this is angle A, and this is angle B, and this is angle C. So the acute angles are angle A and angle B. So we're going to find sine, cosine, tangent of angle A, or sorry, just sine and cosine of angle A, and then sine and cosine of angle B. So if we're starting with angle A, if I want to find sine of angle A, sine is opposite over hypotenuse. So we know that the hypotenuse is always the longest side. In this case, it's AB. So is my hypotenuse, 13. And then the opposite and the adjacent side depend on what angle you're focused on. So angle A, if I try to find the opposite side, I point like an arrow kind of through the angle, points to the opposite side. So my opposite side of angle A would be 5. So opposite would be 5 over my hypotenuse, which is 13. And then cosine of A, cosine is adjacent over hypotenuse. So the adjacent side is the leg that helps create angle A, which would be this side right here, AC. So adjacent is 12, and then hypotenuse is 13. And then that's it. We're good for angle A. So then now we'll find angle B. And then I'm going to go ahead and erase my labeling for adjacent and opposite just because it's going to change if we're changing our angle. So we're shifting our focus to angle B. So now my opposite side of angle B is going to be 12. So AC is opposite of B. So angle 12, or sorry, not angle 12, but 12 is opposite. So for sine of angle B, sine is opposite over hypotenuse, and then the opposite side from angle B is 12 over the hypotenuse is 13. And then for cosine of angle B, cosine is adjacent over hypotenuse, which the adjacent side of angle B is the leg that helps create it, so that would be BC. So 5 is my adjacent leg. So we put 5 in the numerator over 13 in the denominator. And then notice, so without even knowing the like angle measurements, C is a right angle. I should have added that in before, but C is a right angle. And then that means that because C is a right angle, A and B are complementary. That's what we just talked about up here. So if one angle in a triangle is a right angle, then the other two angles are complementary. So C is a right angle, that means A and B are complementary, maybe like 30 and 60, 40 and 50, 20 and 70, or so on. Any two numbers that add up to 90 degrees. And then if we look at the relationship between their like sines and cosines, the sine of angle A was the same thing as the cosine of angle B. They were both 5 over 13. And then the cosine of angle A was the same as the sine of angle B, which they were both 12 over 13. So we can use that kind of relationship to find like an identity when it comes to trig, and that's this section down here. So for a rule, the sine of theta is the same thing as the cosine of the complementary angle. And we'll talk about that a little bit more in a second. And then cosine of theta is the sine of the complementary angle. So a few things that we have to kind of break down here. If you haven't seen this like kind of symbol before, it's called theta. And it's a Greek letter that we usually use to represent unknown angles. So theta, spelled like that. And then this part right here, the 90 minus theta, that's a way of representing a complementary angle. Okay, I think complementary spelled okay. Now I'm looking at it, looks like a crazy long word. But anyways, complementary angle, 90 minus theta, because you know, if like, so let's say theta is, and you don't need to write this down, let's say theta is 30, and then 90 minus theta would be 90 minus 30, which is 60 degrees. So 30 and 60, those are complementary to each other because they add up to 90. So kind of if you have one angle and you subtract it from 90 degrees, that'll give you the angle that would be complementary to it. Okay, so now we're going to take these kind of rules and just compare them back to the problem that we just did. So in this problem, angle A and B were complementary. So if we look at like sine of A was 5 over 13, and that was equal to, so sine of A, sine of theta, and that was equal to cosine of the complementary angle B. They were both 5 over 13. So it's just kind of like one of those patterns that pops up when it comes to these trig functions, but they are helpful formulas to know. Okay, so example 2, what is the value, or what value is equivalent to cosine of 23 degrees? So we can use these little kind of formulas to find those, and I think this is like a multiple choice question in the workbook, so it might have a little bit more context than I added in here, but we want to find like what kind of, I guess, sine value is equivalent to cosine of 23 degrees. I could have written that better. So I would say cosine of 23 degrees is equal to, and if it's cosine of 23, that means that theta is 23. That's our angle that we're working with. So to find what's equivalent to it, since we're given cosine, we're going to use this one right here. Cosine of theta is equal to sine of 90 degrees minus theta, but this time theta is 23 degrees. So 90 degrees minus 23 degrees. In this case, because we're given a 23 degree angle, that's what theta is. And then now to find our final answer, we just have to simplify. So sine of 90 minus 23 is 67, hopefully. Don't know if I'm overthinking that, probably. Yeah, 67 degrees. So sine of 67 degrees. And I guess since we don't have, like we're not subtracting anymore, we don't really need the parentheses. So sine of 67 degrees is equivalent to cosine of 23 degrees. These are equal to each other because sine and cosine of like complementary angles are going to be equal. 27.3 is using trig ratios to find side lengths. So example 1, solve triangle ABC. When you're solving a triangle, that means to find any missing measurement, so any missing angle or side length. Usually it's easiest to find the missing angles first. So in this triangle, we know we have a right angle and we know we have that 60-degree angle up at angle B. So if all three angles inside of a triangle have to add up to 180 degrees, we can use that information to find the last angle. So there's a couple different ways that we can do this. One is by taking 180 and subtracting the two angles that we do know. That'll give us the third angle. So 180 minus the right angle, which is 90 degrees, and then minus 60. 180 minus 90 minus 60 would leave us with 30 degrees. So that means that angle A must be 30 degrees. The other way of doing it is we went over a kind of rule in 27.2 about if there is a right angle in a triangle, the other two angles must be complementary, which means that they add up to 90 degrees. So if I wanted to use that approach, I could take 90 degrees and then subtract one of those kind of other two angles that are not the right angle. So do 90 degrees minus 60 degrees. And that would leave me with 30 degrees also. So we get the same answer either way. It doesn't really matter which way you do it, just whichever way feels comfortable to you is best. Okay, so angle A is 30 degrees. I'm gonna go ahead and just start kind of making a list of what we know. So the measure of angle A is equal to 30 degrees. And then now we need to find two different missing side lengths. So in order to use like Pythagorean theorem, we've used that in the past to find missing side lengths of right triangles. You need 2 out of the 3 to be able to use that formula, and we only have 1 out of the 3 here, so we have to take a different approach. We can set up equations using the trig ratios as kind of like our formula or outline for them. But before we do that, we have to pick out an angle to kind of focus on for our first equation. And you can switch angles if you want, it's totally up to you. So first we'll pick an angle. I'm going to use the 60-degree angle. And it has to be one of the acute angles because the trig ratios are surrounded or kind of based off of the acute angles. So I'm going to use angle B. And then I have to look at what do I know and what do I want to find first. So I know BC. That's the side that is adjacent to angle B, which is 60 degrees. And then let's say I want to solve for the opposite side first. So I want to solve for AC, which is the opposite. So pick angle B, and then I know the adjacent side. I want to solve for the opposite side. I'm going to put a variable there for where the opposite side is. I'm going to call it X. And you could call it X or AC or whatever variable you want. So now the way I set up my equation is I have to pick which trig ratio combines what I know with what I want to know. So I know the adjacent side and I want to know the opposite side. So I pick tangent because tangent is the only one that has opposite and adjacent as its ratio. So I would do tangent is equal to opposite over adjacent. And then I'll go ahead and put my degree measurement for my angle in next to tangent. So it'd be tangent of 60 degrees. So angle goes right here. I could put angle B as well if that's kind of a helpful guide. So tangent of B, but we know angle B is 60 degrees. So tangent of 60 degrees is equal to the opposite side, which that's one we don't know. So we put an X there, over the adjacent side, which is 50. And then now I have a one variable equation where I can go ahead and solve for X. I just have to get it by itself. So right now X is being divided by 50. So to cancel out dividing by 50, I would multiply both sides by 50 because those are opposite or inverse operations. And then multiplying by 50 and dividing by 50 cancel each other out. So on the right side of the equal sign, I would just have an X. And then on the left side, I would have 50 times tangent of 60 degrees, and this is something that we can put in a calculator now. So it may look different depending on what type of calculator you have. You can use like just the Google calculator. If you have a phone calculator, you can use that as well. If you have a regular calculator, it's probably like kind of the easiest way to type in. You're probably able to type it in all in one step. So I'm going to use like kind of like a phone calculator format, so you can see an example of that. If you are working off a phone, I highly recommend putting in tangent of 60 first and then multiplying by the 50 after that. Okay, so your phone has to be unlocked and turned sideways to get like the full menu of a calculator on there. So I would type in 60 first, and then I would click the tangent that just has TAN. There's one below it that says TANH. You're going to put just TAN. So 1.732. That should be what you get for a tangent of 60 degrees. About that, if you get something different, please let me know so I can kind of help troubleshoot. And then now that I have tangent of 60 degrees, I can go ahead and multiply that by 50. So I get about 86.6. So I can go back here. 50 times tangent of 60 degrees is approximately 86.6. And that was when we solved for that opposite side. So I can go ahead and label it as 86.6. And then also just kind of say in my little list down here that AC, that segment, is approximately 86.6. Okay, so technically at this point, because I now have my second side of a right triangle, I can use Pythagorean theorem to find the kind of like third side if I wanted to. But I'm going to use the same strategy as I did here to find that third side, just because I think it's helpful to see like additional examples with that method. The more the merrier. So, okay, let's see. I'm going to show you how... Actually, no, I was going to change angles, but I don't think I'll change angles. Okay, sorry. I'm like deciding what would be best in live time. Okay, so like I said before, it doesn't matter which angle you pick. You just have to focus in on an angle. So this time, just to kind of show that, I'm going to focus in on the 30-degree angle. And then doesn't matter, like we talked about before, how you have to kind of pick out what you know and what you want to know. So I know two sides now. I know the like 86.6 and I know the 50. I'm going to use the 50 just because that's exact and a much easier number to work with than 86.6. And then I want to know the hypotenuse. So let's see, the 50, now that I've changed my angle to the 30-degree angles, the 50 is the opposite side, and I want to know the hypotenuse. It's an unknown. I'm just going to call it y as my variable. So I know the opposite side. I want to know the hypotenuse, so I pick the trig ratio that combines opposite with hypotenuse, which is sine. Sine is opposite over hypotenuse. So I would do like sine of my angle is equal to opposite over hypotenuse. And then I can go ahead and put my angle in for A now. So sine of 30 degrees was the new angle I was focusing on, is equal to opposite, which is 50, over the hypotenuse, which is what we don't know, it's y. So this setup looks a little bit different than the first time we did this problem. And the kind of process for solving it will be a little bit different. What makes it different is that the first part, the kind that's in the pink box, the x, the unknown, ended up being in the numerator of the fraction. And here it ends up being in the denominator of the fraction. So the steps for isolating the variable are just a little bit different. So first I have to be able to get the variable out of the denominator. So I would cancel out dividing by y by multiplying both sides by y. So then the multiplying by y and dividing by y cancels out. And then I have y times sine of 30 degrees is equal to just a 50 over here. And then my goal is to get that y isolated, get it by itself. And right now the sine of 30 is being multiplied by it. So to undo multiplying by sine of 30, I would have to divide both sides by sine of 30 degrees. And then sine of 30 divided by sine of 30, that cancels out. So I'm left with y is equal to 50 times sine of 30 degrees. So now we're ready to kind of put things into the calculator. If you are using a phone one, I highly recommend just finding sine of 30 first and then dividing it by 50 after. So that's how I'm going to do it. So I'm just going to leave the 50 in the numerator and then find sine of 30. So So I'll type 30 and then click sine. It's 0.5. Okay, that didn't work out. It wasn't that bad. Okay, so sine of 30 degrees is 0.5. And then 50 divided by 0.5 is the same thing as like 50 divided by a half, which is like 50 divided by 2. So this would end up being 100. So we ended up with y is equal to 100. So y was kind of the variable we used to represent segment AB. So just to kind of polish off my list, I would say AB is equal to 100. Okay, and then now we have kind of all of our different measurements that we were missing from the very beginning. So we have measure of angle A is 30 degrees, AC is 86.6, and then AB is 100 degrees. Or wait, sorry, AB is just 100, not 100 degrees. It's a line. It's a segment, so just 100. Okay, so biggest thing is that when you're solving these triangles, you have to find all the different measurements in there. When you have just like only one side of a right triangle, you have to use a trig ratio to find the second side. Once you have two sides, you can use Pythagorean theorem if you prefer. I just wanted to do kind of like two of these, so you have two separate examples of them. Okay, so another one of these, this would be like a good time to like maybe pause the video and see if you can get through a problem like this on your own. If you want another example, of course, you can just kind of play it through, just like example 1. So example 2, solve triangle LMN. We have a right triangle, it has a 90-degree angle and then a 67-degree angle. So if I wanted to find the measure of angle L, I know that these two are going to be complementary because we had that right angle in there. So if they're complementary, that means I can just take 97 and I could subtract 67, and that'll give me the measure of angle L, which is 23. So 23 degrees would be the measure of angle L. So we'll kind of start my list there. And then next, if I want to find a missing side length, I need to pick an angle. It doesn't matter which one. It could be 67 or 23. Sorry, it doesn't matter which acute one. You have to pick an acute angle, though. You can't use a right angle. So I'm going to pick 67. And then this triangle is like kind of organized a little bit weird, but we know the hypotenuse here because we know the side that's across from the right angle. So we know the hypotenuse, and now I just need to pick a different side that I want to solve for first. It doesn't matter which one you solve first. Like, it just kind of impacts the way you set up your equation, but there's not really like an easier way or a harder way to do this. So let's say I want to solve for MN. And I'm just going to use MN in this case kind of as my variable instead of like X or Y like I did in example 1. So MN, since I picked angle 67, that 67-degree angle or angle M to focus on, MN is the adjacent side. So I know the hypotenuse and I'm trying to solve for the adjacent side. So I would pick the trig ratio that combines hypotenuse with adjacent, which is cosine. So I would do cosine of angle M is equal to adjacent over hypotenuse. And we know angle M, I can go ahead and put that in for M. So it'd be cosine of 67 degrees is equal to the adjacent side. That's the one we don't know. So I'm just going to use MN to represent it. And then over the hypotenuse, which we do know is 13. And then now my goal is to solve for MN. So I can go ahead and like kind of use inverse operations to get it by itself. Right now I have a 13 that's being divided by it, or no, it is, sorry, MN is being divided by 13. So to cancel out dividing by 13, I would multiply both sides by 13. And then multiplying by 13 and dividing by 13 would cancel out. I have 13 times cosine of 67 degrees is equal to MN. So now it's ready to go into the calculator. Again, if you have like a phone calculator, I would do this part first and then just multiply by the 13 second. So go back to the calculator. Type in 67 first, and then if you have a regular calculator, you're probably typing in the cosine first. It just takes a little bit to play around with it, but just big thing is make sure you're getting the same numbers as me. If you're not, please let me know. So 67, and then I'm going to hit cosine, the one that just has the cosine, not the cosine h, and then after that, I have to multiply it by 13 because that was the number that was in front. So it's about 5.08 8, because if we want to round to 2 decimal places, we would look at the third one, which is a 9, and then 9 would round the 7 up to an 8. So we'll say about 5.08. So MN is about 5.08, and I'll add that to my list. So MN is approximately 5.08. And then we're ready to find our third side. So now that we know like 2 sides, we know the 13 and then we know MN, I can use Pythagorean theorem if I want to, like a squared plus b squared equals c squared, but I'm not, because I just want you guys to have extra examples of the kind of setup here. And honestly, I just kind of like doing those problems more personally. So you never have to use Pythagorean theorem, it's just if you prefer it, you can. Okay, so I'm going to keep the same angle this time. And we know that MN, the adjacent side, is 5.08. I'm going to keep my focus on angle 67 or angle M. And then this time I want to find LN. So I'm trying to find the side that is opposite of angle M. So if I draw a line through angle M, it's pointing at LN, so it's the opposite side. So it doesn't really matter which like known side we pick. However, I would recommend picking the hypotenuse as the side you like know, even though we also know the adjacent side, because the hypotenuse is 13 and it's exact. So I'm going to say I know the hypotenuse and I'm trying to find the opposite side. So I would pick the trig function that combines hypotenuse with opposite, which is sine. So I would do sine of angle M is equal to opposite over hypotenuse, and then I can put angle M in there. So sine of 67 degrees is equal to the opposite side, which is the one that we don't know. So I'm just going to leave it as like it's 2 endpoints, ln, over the hypotenuse, which we do know, that was 13. And then now I just have the one unknown, so I can go ahead and solve for it. So 13 is being divided into ln, so I'm going to multiply both sides by 13 to cancel out the division. Multiplying by 13 and dividing by 13 cancels out, and then I have 13 times sine of 67 degrees is equal to ln, and then I'm ready to head to the calculator. So I'd put in 67 first, and then sine, get about 0.92, and then times 13, and it's 11.97 if we want to round in 2 decimal places, because if we look at the third one, that 6 would round the second 6 up to a 7. So about 11.97. So ln is approximately 11.97, and that was our last missing side. So it's important to realize that depending on how you round, or if you use Pythagorean theorem, you may end up with like slightly different numbers, like very slightly. You should still end up with like the same kind of whole number values, but your decimals could potentially be a little bit off. It's nothing to stress about though. So measure of angle L is 23 degrees, MN was about 5.08, and LN was about 11.97.